Ever since the space race of the 1960s, we have been sending probes from Earth to explore the solar system. Once in a while, the solar system sends something back. This rusty-looking lump of rock has just completed an incredible journey through space. It started out in the asteroid belt between Mars and Jupiter, and arrived here after millions of years adrift. It plummeted through the Earth's atmosphere at unimaginable speed, and was nearly burned away in the process. Finally, it collided with the ground as a blackened meteorite. Scientists have been eagerly examining the rock since its discovery. Even a small sample like this can tell us a lot about the solar system we inhabit. Let's see exactly what we have here. The meteorite feels quite heavy when I pick it up. It has a high density because it contains a lot of metal. I can see it contains metal because one side has already been cut and polished, and it looks like a piece of steel. There is iron in there, which also explains the rusty red color of the unpolished surfaces. Another metal present is nickel. What's special about iron and nickel is that they are both strongly affected by magnetism. Not many rocks from Earth will do this. This is a thin slice from the same type of meteorite, an iron meteorite. Look closely and you can see a distinctive pattern of lines called a Widmanstaden texture. We only see this pattern in meteorites. It's caused by intergrowths of two different minerals, which contain different proportions of iron and nickel. Iron meteorites also contain a few dark spots, which bear non-metallic elements such as calcium, phosphorus, and sulfur. Here we see something very different. It is a stony meteorite. Instead of iron and nickel, its main ingredients are minerals based on silicon and oxygen. At first glance it looks much the same as a rock from the Earth's crust. In fact, it came from our neighbor, the planet Mars. We know that because tiny bubbles of Martian atmosphere are trapped inside, and they match the chemistry of the atmosphere being measured today by robotic rovers. One of the most spectacular meteorites, and my personal favorite, is a mixture of stony and metallic components. In this palisade sample, translucent green olivine crystals are suspended in iron-nickel alloy. It is unlike any material ever formed on Earth. All the meteorites I have shown you so far are examples of achondrites. That means they came from large, solid bodies with internal layers, an outer crust, a mantle, and a core. All the rocky planets feature this kind of layering, and so do big asteroids. Stony meteorites are launched from the crust of such a body when it is hit by an incoming meteor. In other words, one meteor creates more potential meteors. We know this happens because meteor strikes leave behind craters, and plenty of craters are visible across the solar system. The existence of iron and stony iron meteorites implies something even more dramatic. Iron meteorites originated in the cores of ancient planets and asteroids, where iron and nickel were concentrated. Stony iron meteorites were formed by the mixing of core and mantle materials. In order for material to be released from the core of such a body, it must have been fragmented. There may have been dozens of planets in the young solar system, but they smashed each other to pieces, leaving asteroids and space dust behind. In addition to achondrites, we also find chondrites. A chondrite is the most common type of meteorite, but each one is still a treasure in its own right. Instead of shiny metal or irregular crystals, it is made up of circular beads called chondrules. They aren't special just because they are round. You are looking at the oldest solid material in the solar system. 4.5 billion years ago, our solar system did not yet exist. In its place was the pre-solar nebula, a cloud of dust and gas with no structure. Scientists think that it took an extremely energetic event, a supernova, to force the cloud into motion. Radiation from the supernova caused all that dust and gas to start condensing, forming round droplets of matter. Some of the droplets clumped together, and their combined gravity attracted more matter. Eventually they grew into the first asteroids, orbiting a primitive sun. Some of these asteroids never became large enough to develop internal layers, like the rocky planets did. They are thought to be the source of chondrite meteorites. By studying meteorites of every type, scientists hope to understand how the solar system and everything in it came to be. Achondrites can tell us about large, layered objects like the Earth and other planets, revealing details of their history and what they're made of. Chondrites contain information on what the early solar system was like, when today's planets had not even finished baking. It's amazing to think that we can see so far through space, and so far back in time, thanks to lumps of rock like this.